Today I'm going to talk about physical intelligence for physical care. But before I start, I have to say that all the work is done by my wonderful students. I'm just presenting on their behalf. If you haven't visited Ithaca, it's a small town in upstate New York. Please come. Summer is a beautiful time to be there. This is us just after a lab barbecue in a park over there. All right. So in general, what our lab does is we develop what we call like a full stack. I'm trying to develop a full stack physical robot caregiving ecosystem. So you can think of this as in 2D like a triangle, 3D like a pyramid, where on the top lies various applications or activities of daily living, such as robots feeding people, people with disabilities, mobility disabilities who cannot feed themselves, robots dressing them, robots bathing them, transferring them from bed to wheelchair and things like that. Now to support these applications, obviously we have to develop various algorithms and systems. So I call this as the middle layer. And then on the bottom, what we call this like a research toolbox, where we have developed various toolboxes like simulation platforms, data sets, libraries that are being used by multiple groups around the world. And these support algorithm development, system development, as well as application development. So to start with, right, like building physical caregiving robots is very challenging. And the reason is that it's a very contextual thing, right? It is contextual on the user. Every user is different. Not only because their physical, the kinds of mobility limitations they may have is different, but also their preferences may be different. Their environment may be different. So the kind of assistance that you get depends on the environment that you are in. The human caregiver, like what can that human caregiver do? Formal versus informal caregiver, as well as the robot embodiment. Now just to clarify, while there are various robot embodiments that are there, in my lab, we focus mostly on robot arms, like the one that you see this end. These are mounted on wheelchairs or other assistive devices, and they can move around and like do tasks. Now, in general, as roboticists or as a computer scientist, like our goal, our vision, grand vision is to build Rosie the robot, a robot that can generalize to every task that there is, right? But if you think from the caregiving perspective, for a user to actually accept this robot as a part of their daily life, it needs to feel very personal. The user needs to feel like the robot is built for them. And there is this very interesting trade-off between generalization and personalization that you need to think of, right? That makes it, again, very challenging. So the way I am going to talk about this, it's not going to be possible for me to talk about every project that there is in my lab. But I'm going to focus on mostly two ADLs. One is robot-assisted feeding, which is probably the most mature line of work from our lab because we have deployed this in people's homes. And also robot-assisted transferring. And then I'm going to end the talk with a very quick overview of some of the other projects that we have done. So robot-assisted feeding. What do I mean by this? So here is a robot. As I said, this robot is mounted on a wheelchair. Here, everything that you see, the robot is doing this autonomously. In this case, it picks up a fork. It can be a spoon. It goes on top of a plate. Algorithms on the back end not only identify what food items there are, but how to pick it up. It uses both haptics and vision to pick it up in a way that it does not destroy the food item. And then it goes in front of a person and then feeds them so that it's easier for them to take a bite. So in this case of a carrot, it actually tilts it so that it's easier for them to bite. To be very transparent here, this person does not have any visible mobility limitation that we know of. This person was just an undergrad that we got in this wheel to sit there and do this. But I'm going to show you that how we have actually worked with real users and deployed this in real homes. Now, the reason I want to show you this video is to show that the way we have dealt with this robot-assisted feeding problem is we have divided this into two phases. One is bite acquisition, which is how do you pick up a food from a plate, and then bite transfer. How do you transfer food to somebody's mouth? So let's look at bite acquisition first. right? I'm going to talk about the different technical aspects of how we actually develop these systems, but it's not going to be possible for me to really do a very deep dive, and you can ask me questions for each of these. So now for bite acquisition, basically, like here is an example, right, of our bite acquisition system. Like here we have been able to, pick up various food items. Some food items we literally went to Wegmans. I mean, if you're not, Wegmans is a chain grocery store in the Northeast. Literally went there, got the food, put it on the plate. There are some home-cooked items, and there are some other, items, like food plates. And the robot can pick up these food items while also catering to their to users' preferences. How have we done this? Let's walk through an example, right? So first, basically the algorithm, in a very quick overview, basically what happens is there is an initial image, like a plate. Robot, the camera is on the robot. Everything, we don't instrument the environment. Everything is on board. So the robot goes on top of a plate. It identifies using VLMs, visually conditioned language models. Think of this as multimodal language models, where LLMs are just language models. They identify different food items as well as where they are. That goes as an input to a structured task planner, whose output says, how many actions do I need to take to pick up this food item? It comes up with an efficiency score. That score goes to a downstream large language model, which also takes in a user. Let's say the user says, please don't feed me meatballs in this meatballs on spaghetti dish. Then it uses chain of thought reasoning to actually pick up the items according to users' preferences. So let's see. User says, please don't feed me any meatballs. Now the robot starts. So first it starts to remove the meatballs. It failed. It detected it. And it kept doing it while the meatballs are out. Then it twirled the noodles, picked it up. Next time, it figured out that there are not enough noodles to pick it up. So it grouped the noodles so as there are enough noodles, and then it twirled it to be able to pick it up. So all of this thing is done autonomously using these large models, visual language models, as well as large language models, chain of thought reasoning. But did we solve it? No. There are various failures. Failures still happen. One of the things we identified that this happened was that all these visual language models and large language models were mostly reliant on just vision alone. And if you think about eating food, it's also a very, you feel what you are touching, right? Like for especially wide number of food items that can, meals that can happen. So for that, what we try to extend this work is by saying, okay, let's add what is called a skill affordance, which is a tool affordance. What can a tool do? And food affordance, which is what does a food allow? So for tool affordance, we basically had some kind of offline tool calibration. So various kinds of tools, what is their success rate for different food items? And for food affordance, initially we start from a common sense of VLM, and then we update it. So let's look at this. The robot is trying to pick up this chicken nugget. It goes to a GPT property which identifies some physical properties, and then GPT skill, a planner, says, okay, I should skewer. Robot starts skewering it, and it is successful. Great. While skewering it, now, when it touches it, it can feel. It can collect also force data, right? So using that, basically the GPT property again says, okay, let's skewer. Tries to skewer, it actually fails. Because in that short amount of time, actually, it cooled down, the properties changed. But now, because you have haptic data, using this, it updated the physical properties, the softness, moisture, and viscosity value. And that let the planner say, oh, instead of skewering, you should actually scoop it up. And so then it kept updating these things using online updates to be able to pick it up. Even with this, it improved success rates, but it was not the end of story. Because even after that, there were failures. LLMs hallucinate. All kinds of things can happen. So that's where we thought, okay, to really make these systems come in people's homes, we need to have human in the loop. Now, generally, when we think of human in the loop, we always say, okay, if my algorithm says, okay, I don't have a lot of confidence in the task that I'm going to do, let's ask a human. But here, every query that you ask a human also imposes querying workload. So how do you balance between these two objectives to be able to basically do the task properly, but without actually imposing too much querying workload? So to do that, first we collected a lot of data of different kinds of querying failures that can happen in this feeding scenario, and different kinds of feedback that a person may need to give. We looked at all of these independent variables. We collected data with people without mobility limitations as well as with mobility limitations. And then based on that, we developed a querying workload model that can say, given the kind of query and the history of interactions, can I predict what your querying workload would be? Using that, we developed an algorithm, which we call it linear upper confidence bound query gap. Basically, the insight is very simple. Let's say there are various actions that the robot can take. I take the best action, and I see what is my least confidence, or like my lower bound of achieving the success rate for this. I take that, and I take the next best action and look at its upper bound. That is my what I call a pessimistic gap. This pessimistic performance gap, if it is greater than a scaled version of my predicted workload, then I will decide I have to query, otherwise I will not. So based on this, what happens here is on the left, there's a person without any mobility limitation, and you see that when the robot fails, it immediately queries the person, and then when the workload goes up, but it is able to successfully finish it. But now, on the right side, when you see this person with multiple sclerosis, when we're feeding them, it fails, but it doesn't ask the person. It continues to fail, and after a certain point of time when it decides to actually ask. What does that mean? The insight is, because for a person with multiple sclerosis, answering the query for this particular person imposes more querying workload, the robot decided to sacrifice task. They said, okay, maybe instead of taking 2 minutes, it will take 3 minutes for me to empty the plate. But it's going to impose less querying workload, and that leads to overall task satisfaction. So considering user factors are very important when we deploy these systems. So once we had this, we thought, okay, we have tried our best to make these robot, or like the algorithms pick up these food items, as well as have human in the loop while considering this workload. Let's move on to the other part. Like, okay, once we pick up, feeding is not complete, right? We have to actually feed somebody inside the mouth. So when we did that, we basically wanted to go to this bite transfer part. There we found out that it is an extremely challenging problem because many people, when we tried to identify the needs of our target population, right, we found that many people who require an inside bite transfer have very complex medical conditions. So for example, this person with spinal muscular atrophy has a very narrow mouth opening, which means for a robot, there is no obstacle-free path. Like when you think about robots, or let's say self-driving cars, the entire, most of the community thinks about, okay, all of the objects in my environment are obstacles, I need to avoid contact. There is no solution here while avoiding contact. You have to come in contact, right? This person with schizencephaly has very poor jaw control. This person with arthrogryposis can only chew food from one end of their mouth. They use their tongue to guide, a caregiver or something to tell where to. This person with multiple sclerosis has involuntary spasms. Imagine a robot with a fork coming, and then suddenly you have a spasm, right? This work took us a long time, almost 1.5 to 2 years, to make sure the systems are safe enough that we can deploy this in people's homes with various levels of safety, which I'll come to that later on. So the way we achieve this very quickly again is basically we developed a new perception method, which we call femto, which basically works even under occlusion, because the thing is, when you come very close to the mouth, even your own robot is occluding the camera's view. So you have to work with occlusions and predict the mouth state. And we have to classify different kinds of classifications. When there is a collision, when there is a spasm that is not meant so that the robot should ignore, versus when there is an intended contact where the person is using their tongue to move a 20, 30-pound robot, and then it has to be compliant enough that they can move with their tongue, but the robot needs to understand, oh, this was intended. This was not a spasm. So next time I should remember that I should feed on that side. So once you identify these things, like we implement this, and then we actually fed people with different conditions: arthrogryposis, multiple sclerosis, different levels of spinal cord injury, schizencephaly, cerebral palsy, in a hospital, in somebody's home, as well as in our lab. There's one particular video I want you to pay attention. This was this wonderful girl. Like she has schizencephaly. It's her father. Mother is in the background. Okay. This happened. Mother started crying during the process. It's like for the first time she was able to feed herself. She feels empowered for this, right? Now again, these systems are still not ready to be deployed. We are still very much in research process. But these kinds of feedback helps us continue to give us motivation to keep working on these kinds of things. So taking these systems of byte transfer and byte acquisition, we wanted to actually go to a real home deployment. And there, before going there, we understood, again, as I was mentioning, every user is different. They have many different personalization requirements, right? And one thing to be very, like in these kinds of cases, right, nobody wants to be just sitting on a wheelchair and the robot does everything for them. They want to feel like they have a sense of agency. Otherwise, technology acceptance is not going to happen. Humans need to be a part of that technology, right? And so what we did was, before deploying this, we actually did a formative study with 17 care recipients. And we found, even for just this one task, this feeding task, like there were like 46 different user preferences that they said, even with just these 17 people, right? So it's like scaling it up is a extremely challenging problem. And so we identified this, and then so we developed this system where our system, which we call Feast, is able to do 36 out of these 46 preferences. And also, we followed this IEEE ISO standard safety requirements for personal care robots, as well as IEEE standard for transparency of autonomous systems. What is transparency? Transparency basically means, like in this case, the person understands what the robot is thinking. And that helps them not only gain trust, but also adapt the robot's behavior. And so our system can do from level 1 to level 5 with different levels. I'm not going to go into too much into details of this, but you can ask me questions later if you have. So basically, the system is like this, right? The person, initially we have this robot, and then like it has various inputs. It can have a voice input, button inputs, LEDs, gestures that you can design. A user can design on the fly, right? Like with the robot, we are taking the robot in a person's home, and then the person trains the robot to say, oh, I can give these gestures given on my mobility. Can you use these gestures to do certain tasks? So you design these gestures on the fly, and then use language and other things. And based on this, the person gives an input to say what kind of behaviors they want from the robot. And then downstream, we implement these using a library of skills. Each of these are modeled as behavior trees. And then a downstream low-level things, we have like simple motion planners and different kinds of controllers. For safety, we have five different levels of safety, from like high-level safety to even like hardware-level safety. Now, here is an example of a live interaction. So what you see here, this person uses what you see there, over there, you see a web interface using this pointer. They obviously cannot use their hands, so they have a nose tracker using which they interact with digital technology in their homes. Basically, we just came, the person said there is food inside the refrigerator. The student brought the plate there, and now everything is done by the robot. you'll see the person obviously wants to watch TV while it's being fed. It wants to be hydrated, and sometimes mouth wiping. The robot will do everything. There were 2 interventions by my students. One was the food was cold, so my students went and heated it up in a microwave. And second was, at one time, this nose tracker stopped working, so they had to refresh. These were the only 2 interventions. Otherwise, everything that you see was autonomous from the robot with user input. And here, I wanted to highlight one thing, why transparency is important. LLMs, we were using large language models. LLMs hallucinated. This person basically said, I don't want you to, for picking up a food, I want you to wait for maybe just 2 or 3 seconds. But when you are feeding me, wait till I finish chewing, so wait for at least 10 seconds and then feed me. LLM hallucinated the instructions, and it started giving this input to 10 seconds to all the steps. The person said, next bite, it's doing something that I did not ask. Person asked the robot, why are you waiting? Robot, basically the LLM robot said, because this is the time that you asked me to do. No, I did not ask you to do this. I actually asked you. So after 2-3 interactions, think of this in a crude way of saying, having this transparency adaptability loop made the person an expert prompter. So it could get the behavior that you'd want it to. So for any task, whenever we think about adapting to a user, it's also important for the user to understand what is going on. Otherwise, they won't be able to adapt it to the kinds of things that they want to, right? So this is mostly on robot-assisted feeding. I also want to briefly touch upon another application that we are looking at, which is transferring. Whenever I talk to stakeholders, one thing that everybody said is that, yes, feeding is important, but it is for people with very severe mobility limitations, this is something that they cannot do. But one of the widely people, almost everybody asks for a need is to be able to transfer them from bed to wheelchair or something like that. Now, the issue is the following, right? Like Henry Evans, this person with hemiplegic stroke, basically says that the reality is that any robot strong enough to lift a human is strong enough to be dangerous. We have robots that can lift cars, but those are in factories, in work cells. Humans don't come close to them. If we have a robot that can actually lift a human, it can be dangerous, right? So how do we really develop robotic solutions? I've been thinking about this for quite some time, and then we came across with a solution where the idea is basically using assistive devices that already exist in care recipients' homes. What do I mean by this? So for example, this is a Hoyer sling lift that some caregivers use for transferring, where basically this is a mobile base, this is a sling bar with hooks, this is a sling sheet with various straps. And generally, when a human caregiver does this, basically they push the sling on the bed, and then they actually tie the sling strap on the hooks, and then they move the wire sling and then place them on a wheelchair. We wanted to see, can we do this with a robot, but also leveraging these assistive devices, which are manually controlled. There are electric wire slings, but that's mostly for lifting, right? They cannot move on their own. So what we did was, our key idea was, one of our care recipients, again, Tyler Schrenk, C1, C2 spinal cord injury. Unfortunately, he passed away just a few months back, but he has been an extremely, an amazing collaborator for us. So this care recipient, he basically said that you can put, they're okay with, lying down on a sling sheet. So we thought, okay, then the first problem we should target is not human body manipulation, but actually picking them up and placing them. So the key insight was, let's use an instrumented assistive device because they have high payload capacity to lift people and do coarse positioning, and use robot arm to do finer manipulation, intricate manipulation. So basically what we did was, we developed this kit called Chariot Kit that takes commercial products, commercial wheelchairs like Permobil, Quantico, all the 3-4 more widely used wheelchairs, We instrument them with sensors, actuators, compute, make the customer modifications, and we make them instrumented assisted devices. So wheelchair modifications, so now the wheelchair can be controlled by a robot, it becomes autonomous, as well as the Hoyer sling. And so now the Hoyer sling also becomes autonomous and it can control. So now each of this becomes a robot, and then this becomes a multi-agent coordination problem. So now we use the robot arm to actually do intricate tasks such as tying the sling sheet. And so but this is also a very difficult task because it's very deformable. And while you try to do this, the sling can move. And so, if you want to really try this out, you can try this out. We have a special see how difficult it is for you to do this manually. So the way we did this is, again, it's kind of a busy slide, but I'll just give you a high-level insight. The high-level insight is that we use a turn-taking multi-agent model predictive control. What that means is we have a robot that is the leader, the robot arm, and then the assistive devices, the wheelchair, the Hoyer sling are, basically are the other agents that the robot is controlling. And at every turn, each of them decides what to do so that the overall objective of picking up a person and then placing them is achieved. We model the perception using key points, and then we use something called a model predictive control to basically decide, if I take this action and in future it's going to go like this, maybe I'll take the first action this way. And I keep optimizing for it over time. And there, basically, the idea is when we think about tying it, we use a method from knot theory, where the idea is you can quantitatively measure how you can tie two different things. So once we did that, we actually tried this in simulation, our own simulation that we have developed. And it works, but nothing is real unless it works in the real world. Now, this is where I want to mention that our transferring work is not as mature as our feeding work. So what we have done is this. We have done this in our lab with a mannequin. I have been transferred. My student has been transferred, but we have not tried with people with mobility limitations yet. We are actually going to try this in the next couple of months. But this is to see the system. I'm going to show you. This is how it works, right? So first, the mannequin is lying down. Everything that you see is autonomous. So what you see here is that the robot tied the sling, and the Hoyer sling moved its sling bar so that it's easier for the robot to tie. Then the robot automatically with the wheelchair went this way. Now, to make it easier for the Hoyer sling automatically moved. Everything is autonomous, multi-agent coordination. Then the robot picked up this sling sheet, sling strap, and then again to tie it was a multi-agent coordination between the robot's arm and the Hoyer's the sling bar. And he kept doing this for all the slings until all the sling bars are tied. And then it will come back again here. When it comes back here, again, to make it easier for the robot to access this sling bar, which is on the other side of the bed, the Hoyer sling moves on this side. So again, it is done through this multi-agent coordination scheme that I was telling you. And then finally, it ties the fourth strap. Once all the four straps are tied, again, coordinate sling bar rotation, then the Hoyer sling, this goes away. It picks it up, and then it goes. Now, obviously, see a lot of vibration. So what we are working on now is using the robot arm to stabilize this. Well, because with a human, that's not realistic. And then it goes there and then gently places the mannequin over there. So this is, again, like some preliminary work that we have done in the realm of transferring using multi-agent coordination. But there's a lot of work to do. This is just preliminary. What I'm going to do next is I'm going to cover a couple of other projects that we have done on a very high level, just to give you the breadth of work in this domain in physical caregiving. So the first thing I want to tell you about this work, which is called GRACE. The main idea was that, let's say I have, every user is different, I mentioned, right? So what that means is, let's say there is a person, I deploy this in a person's home who has multiple sclerosis versus a spinal cord injury with different levels of spinal cord injury versus this. If my feeding system knows how to feed this person, can it automatically generalize when a new person with different mobility limitation comes in? So the idea was that, can we somehow represent the mobility of a person so that the robot can use that knowledge to generalize the robot policies for that? And when we do this, basically the idea what we are doing is that we are using basically occupational therapy scores, like functional range of motion scores, as well as kinematics. And we come up with a latent representation of a user's mobility that says whether a particular configuration is feasible for the person or not. And based on that, let's say the robot decides to give minimal assistance that's needed for the person. So let's say I have this laser pointer, and I'm trying to do a handover task with somebody. Now, if I know that I have an idea of where all the person can move, the robot goes and gives minimal assistance so that the person is encouraged to move more to be able to capture. Versus a new person who may not be able to move, the robot gives the appropriate amount of assistance. So the assistance is personalized to the user's ability. That is what is the point of this particular work, which is user ability aware robot caregiving. If you're familiar with this, these are various ARAT tests and other tests that we did to do this. Another project I want to introduce you is this simulation platform that we developed called Arcare World. The main reason why we started developing this was basically when I joined Cornell, I realized that to be able to really do meaningful work in this domain, not only we need access to expensive robots, which I can get because of my startup or something, but also need access to care recipients, caregivers. And this is where, in a small town like Ithaca, it becomes very challenging. So I was trying to see how can we democratize this field so that we can actually enable people who don't have access to this to give them a simulation environment with humans, proper human models as well as robot models, right? And so the idea was that in this Arcare world, we actually have people like our occupational therapy collaborators. They went into people's homes, they went into hospitals and measured with occupational therapy scoring, like MMTs, various kinds of scoring they did to be able to capture a person's mobility, as well as we developed musculoskeletal models for each of these people. When we released this Arcare World simulator, we released this with 6 avatars, but as long as you have data, you can build your own avatar of a person with mobility limitation. We then also have robots, and we have also assistive devices in various assistive environments. And this allows us to run simulations before we deploy this in the real world. So using this, actually, just last couple of months back, we did this competition called PhyRC, Physical Robot Caregiving Challenge at ICRA, which is a robotics conference. So the first phase was 56 teams from 17 countries participate in the phase 1, which was the simulation phase. And then we selected top 5 teams that advanced to phase 2, which is the real world phase. They brought their robots and they tried to do bathing task and dressing task with a mannequin in the conference. And the winners for each of these tracks get a robot for free. So we were lucky to get good sponsors for this. So we are trying to democratize this even more and more. Finally, this is this physical caregiving data set that we have captured with occupational therapists coming to our lab. We have captured, not only their motion, using motion capture, but also, when they do physical caregiving, using language, gaze, eye gaze, where they are looking, how much force they are applying to the mannequin. So the mannequin is covered with an artificial skin that we have developed. So we are not only capturing where they are touching the mannequin, how much force they are applying. So we are collecting this huge multimodal data, and the idea is that to use this data, this is going to be open source in the next month, and then to use this to learn robot policies. And then here are some other projects, like robots bathing people with multiple sclerosis, robots doing meal preparation, robots basically doing whole arm manipulation, or even other things. So to conclude, I want to end with a key insight. of our deployment. First is stakeholder engagement is very important. Not just, okay, we have developed algorithms and systems, now I have to evaluate this to publish the paper, I go to evaluate with users. That's not the path to success for meaning. The engagement is important from the beginning, from the inception of the project itself. Generalization versus personalization. Our recipe is out-of-the-box generalized system as much as possible. Then when we deploy, a 5 to 15-minute calibration step, and then in the wild personalization. Personalizes the behavior on the fly. System infrastructure needs to have a modular software design so that it can go across multiple robot embodiments. And we try to leverage foundation models because of its open world nature. But for failure recovery, we always use humans in the loop. Again, caregiving is very contextual. Even if you don't remember anything from my talk, this is the key thing that is important. Us as roboticists, as computer scientists, many times I even try to invent problems that may not be actually needed. That's where connecting with stakeholders, I have weekly meetings with occupational therapists. It's very important. And that's it for my talk. Thank you.
Thank you. Maybe we can take one question. Only one question, and then we'll defer everything else to the panel that we have. Okay. Is there one? Okay, yes.
Thank you so much for the talk. Really cutting-edge technologies that you guys are developing. My question was, you mentioned that you're collecting a lot of different data points from these occupational therapists, and you mentioned that these are going to be used to inform developing new robotic technologies. Do you envision that these data points could be utilized, and this might be different from what your goals are, but to help train caregivers as well?
Yes, absolutely. So actually, when we first deployed, when we first introduced this RCare World Simulator, one of the first groups that reached out was a nursing school and occupational therapy school, programs. They said one of their biggest pain points is field training. And so they said, before you actually go to field training, we can create this simulator, simulated conditions there, and then they can learn caregiving in the virtual environment using VR and things like that. And that is not the end all, but that is a step towards going that. So yes, absolutely, I agree with this. Thank you.